Okay, hi everybody. It's always a pleasure to be back in this room speaking here. Actually, if any of you have ever been on my webpage, the picture there is in fact like right here, a panoramic photo shot by our own Emmanuel Kowalski, one of the organizers of this seminar. But in the picture, there's like multiple versions of me, like in a Marcel Duchamp painting, because he used the pano feature on the iPhone while I was walking. I can't quite reproduce that effect in real time, but oh, now I need chalk. So where is, oh, over here, okay. Okay, so let me kind of try to make a sales pitch for geometric analytic number theory. And often, first of all, those of you who have heard me talk lately, I'm going to talk about some new results, but somehow I feel like a long time ago I figured out a good 20 minutes of introduction to the themes. So some of you will have heard the first 20 minutes before. If you've heard me talk about this kind of stuff, it's going to be mostly the same. But somehow, sometimes I have to explain what analytic number theory is. But for this audience, I don't. So maybe I'll try to explain what geometric is instead. So let me sort of explain, before I even talk about any math, the general strategy of what I mean by geometric analytic number theory. So you start, step one is some question in analytic number theory, and most typically, this is going to be a question in the subfield called arithmetic statistics, which essentially means we're just going to count things in the way that Philippe talked about this morning, with an emphasis not on exact counts, but on the asymptotics of countings of various arithmetically defined things. And usually this is going to be over Z, right? We're going to ask questions about integers. So step two is going to be to replace that question with an analogous question with Z replaced by a different kind of ring, a coordinate ring of a curve over a finite field. And to make life simple, and everything I'm going to talk about today, I'm going to talk about simply the ring of polynomials in a single variable over some finite field FQ. And the analogy between integers and polynomials over a finite field is very old and has been very productive, at least for getting ideas in all kinds of number theory. And in the example I'll do in a minute, for those of you who are not familiar with it, we'll see exactly how that analogy works. I mean, besides like that they're both rings. But this is not geometric yet, right? This is what you might call analytic number theory over function fields, the subject of a AIM conference. Where's Chantal? That Chantal and I organized just a couple of years ago. Hello, there's Chantal. Okay, so this is step two. We've sort of come to that, analytic number theory over function fields, but it's not geometric yet, okay? So to make it geometric, we push the analogy further. But now that we're studying a ring of polynomials in one variable, we say, why should I restrict myself to a finite field? I can think about polynomials over any field. And in particular, if we're going to do geometry, the best field is the complex numbers, so that's what we should use. So now we'll replace FQ parentheses T replaced by C brackets T. But now we also have to replace the word counting, right? Because C is good for some things, but it's very bad for counting things. And so counting is going to be replaced by some form of geometry. And in a minute, I'm going to sort of show you in a very elementary example, like I'm going to sort of, I'll show you this strategy pushed through start to finish. But the theme, I mean, and then I'll talk about some new results where this theme has been used to generate new results. And it really is kind of fun. I mean, you can, of course, the most famous example, by the way, that you guys probably know about is, of course, geometric Langlands, right? Which is sort of very much, you start with the Langlands program that we all know from the 60s and 70s, which concerns automorphic forms over Q. There was later the development of the theory of automorphic forms over function fields. And sort of, I guess, sort of at the same time, the completely geometric story, geometric Langlands, where you really talk about fundamentally different kinds of objects, but that are somehow analogous. And everything takes place over literal curves over the complex number. So in some sense, what you should think of the process as being is you can take almost any number theorist's name and then put the word geometric before their name, and then you can be talking about some problem in topology that that person probably would not recognize as being related to their own work. And so that's what we're going to do to various number theorists over the course of this talk. Okay, so let me start. I got to start with an easy problem, right? So let's start with an easy problem. But again, in the kind of counting vein that Philippe mentioned, you want to sort of count integers subject to certain kinds of constraints, let's say on their factorization structure. So let's ask, how many integers in the range between x and 2x are square free? Okay, maybe I'll make a little chart over here to sort of think about this question. So here's z, here's fq brackets t, and here's c brackets t. Okay, so let's start with the interval between x and 2x, and number of integers in this interval which are square free. Well, we know the answer to this question. It's a positive proportion. The size of the interval is x. Maybe I'll even write that in here. Is zeta of 2 negative 1 times the size of the interval, and then plus something smaller. I guess it's like O of square root of x or something like that. Okay, of course this is 6 over pi squared. So speaking loosely, I mean, we would say the probability that a random integer is square free is 6 over pi squared. Okay, so that's a question that, I mean, I'm not going to sort of go into the analytic number theory of that. I think we all know it. What if instead we think about fq brackets t? So already, at the very first moment, if you haven't thought about this analogy before, you face an immediate problem, which is what's an interval? Right? I mean, the polynomials are not in any particular order, but that's okay. I mean, what we should think of is this interval you should think of as the set of integers whose Archimedean absolute value is about size x. So here, what's the analog of Archimedean absolute value? You need some function from this ring to the real numbers, which is multiplicative. And if you like the theory of Dedekind rings in general, somehow you know what this should be. And if not, you can just guess what it should be, because there's only one good function. It's given to you by the degree. But then you're like, oh, wait, the degree, it adds when I multiply polynomials. It's not multiplicative. So I just exponentiate it. So let's say the size of f, now I have to define it, is q to the degree of f. And now I have my nice absolute value. And now my interval is going to be all polynomials which are of about the right size. So I want, so now this looks a little nasty, right? Because I want the degree to be log base q of x. I certainly don't want to write that down. So let's say, let's just take x to be a power of q, since that is the value of the absolute, that is the kind of value that the absolute value takes. And then our interval is going to be the set of polynomials polynomials of a fixed degree n. Now I left a little bit of space here because I have to fix this a little bit. See, nobody yelled it out. This is not the set of integers whose absolute value is about x, right? That would be this union with its negative. So if you like, just sort of for convenience sake, it's simpler if I sort of eliminate the ambiguity of the units of z. I want to sort of get rid of that ambiguity of -1. Similarly here, I want to get rid of this ambiguity of the units in this ring, the fq star, and in order to do that, I'll just make f monic. Okay, so f is a monic polynomial of degree n. That's sort of the analog of a positive integer in that range. And how many of them are there? I mean, it's easy to see that there are q to the n f in this interval. Okay, so that's good. That's how we know we got it right, because there's about capital X. The size of this interval is capital X, and the size of this interval is q to the n. So our analogy is in perfect working order so far. Okay, there is a clock here that I can see. That's good. It's sort of faded into the background there, but I can just see it. Now, how many of these are square free? The number of these which are square free is q to the n minus q to the n minus 1. So it's the same answer. I don't know if it immediately looks like the same answer, but any difference between these two answers is completely cosmetic, as I will now remind you. I mean, again, note that this is a positive proportion of all the polynomials in this so-called interval. So shall I continue over here? This column's finished. Here's column 2. That's 1 over 1 minus q times q to the n. But of course, this is again zeta 2 inverse times q to the n, but this zeta 2 is not the Riemann zeta function. It's the zeta function of the affine line. So it is the zeta function of the ring fq brackets t, which you can define in the exact same way as an Euler product of local factors formed from the irreducible polynomials, in the same way that the Riemann zeta function is formed as a Euler product of local factors corresponding to the primes. Okay, so here we have an analogy that's very nice. And now but we're not geometric yet, right? We're in sort of part 2. So what's going on over here? What happens in the geometric story? Well, our interval is still going to be f monic in C brackets t of degree n, and now we need to study those polynomials which are square free. But now, as I said, counting them is definitely the wrong thing to do if we're working over an uncountable field. So let me give a name. Let's say conf n c. Well, I could write it's the set of square free polynomials. But I'm not going to write that because it's a space. And if God gives you a space, you should call it a space and not a set. So this is the space of square free degree n polynomials. So we can write this in a few ways. We can think of it as just polynomials of the form t to the n plus an minus 1, t to the n plus dot 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 a naught, such that, I mean, a polynomial is square free if and only if its discriminant is non-zero, right? So the discriminant is going to be some crazy function of the coefficients, which everybody in this room knows for a quadratic polynomial, and no human knows for any polynomial of degree higher than 2, but it is something you could like put in your computer. It's some polynomial in these coefficients. So that's one way to think of it, but not really the most useful way for our purposes. I want to think of it as a different way. It's a all right, I'm going to say the word moduli space. Why not? The moduli space of unordered n tuples of distinct complex numbers z1 through zn. And why is it that space? Well, I can take a polynomial and assign to it its roots, right? So p gets sent to the set of roots of p, and the condition that p is square free is exactly the condition that the roots are distinct. And of course, the roots don't come in any particular order, so what you get out of p is an unordered set of n distinct complex numbers. Okay, so here's an analogy. Here is a thing, comp NC, a space which has something to do with the problems at the left, but I haven't said what we're supposed to do with it, right? Since we're not counting it. Well, we're going to take its cohomology, okay? Is everybody still here? Okay. We're not going to say, I'm going to try to kind of black box all the cohomology in this talk, but I do want you to know it's there. And in this case, actually, we can talk about it quite concretely, because there's not too much of it. That's the key. So compute its cohomology. That's the algebraic geometer's version of counting. Am I supposed to use this little thing or the regular eraser? Does anyone know? Okay. It's good the organizers are here to help me know what to do. So I have a choice. I can either tell you why I'm going to compute the cohomology of this space, or I can just compute it and then tell you why. And I think I'm going to do the latter and first talk about what it is and then tell you why I care. All right, I think I'm going to say not too much about this. Let me just say the following. So here's a theorem of Arnold, which is that hi of comp NC with rational coefficients, and I'll tell you what this is in some cases, what this means in some cases in a minute for those who don't spend their life immersed in cohomology. This is equal to, well, let's write it like this. The H0 is Q. Okay, H0 I can tell you all about. H0 is just a vector space whose dimension is the number of connected components of this space. So that's sort of the most basic topological invariant you can imagine. And so what I'm saying when I say that it's Q, that it's one-dimensional, is i.e. comp NC is connected. And I mean, just in case you've never thought about this, let me just convince you that that's true. I mean, a configuration of 4 things looks like this. A different configuration of 4 things looks like this. If I want to get from here to here, I can do that with a continuous motion, right? Because points, the complex plane is kind of a big place, and points can move around each other. If I were doing the configuration space of a line, it would be a totally different story, because points can't move past each other. But here, we're OK. So if anybody in the room has never computed a cohomology group before, now we just computed one. OK, great. What's more, OK, H1 of comp n Q, this is also Q, at least once n is bigger than 1. OK, H1 is a little bit more subtle, but you should think of it as tracking loops in the space. So a loop in configuration space is a way of starting with a configuration and sort of letting it move and letting it move for a while until it comes back to its original configuration. OK, what does that look like? Let me draw a picture for you. The only way I can sort of ever think of this is by sort of thinking of it as like a movie where time is like the vertical axis. So I'm supposed to be moving from this configuration back to itself, right? That's what a loop means. And so at each stage, I've got a configuration. And what happens? This point is like moving around. and it ends up here. This point is moving around. It's got to get back to one of these other points. It doesn't have to go back to the same point, because remember, there's no ordering on these points. But it's got to end up at one of these points. But now there's a problem. Right at this time slice, remember, at each time slice, it has to be a configuration. The points must be distinct. So what that means is these strands I'm drawing are not allowed to cross. So it's got to either go in front or behind. Let's draw it behind. And then these other guys just do whatever they do. And this is, of course, a picture of a braid. So in some sense, underlying all of this is the beautiful story of Artin's braid group. I'm not going to talk about it so much today, but that's sort of really what is driving this space. And it turns out when I say that this H1 is one-dimensional, I'm sort of saying really the only kind of loop that you have in this space is two of these points like winding around each other. And that's sort of the only thing that can happen. And now, OK, let's think about H2. And you're like, oh my god, that means like a sphere embedded in this space, and somehow I have to think of like about a two-dimensional family of these configurations, and it seems very hard to draw. But here's the good news. You don't have to think about it, because it's all 0. That's how Arnold helps us. OK, so hi of conf nc on Q is 0 for all n. Another way to think about this, by the way, is it's sort of fun to think about what these configuration spaces are for very small n. For instance, n equals 1. OK, that's easy, right? That's like unordered sets of one complex number. OK, well, that's just a complex number. So conf 1 of c equals c. If you like, this is the most pretentious way in the world to describe c would be it is the moduli space of square-free polynomials of degree 1. Well, it is, right? Because it's like t minus something. OK. What about conf 2c? That's a little bit more subtle, but if you think about what it could be, OK, there's going to be 2 points in the space. You can imagine that by translation, I can sort of always imagine one of the points to be fixed at 0, and then the other one is just kind of going around it. So OK, I cheated a little bit because I thought of them as being ordered. What I sort of said was like, oh, this space looks like a circle, right? One point is fixed, and the other one is just moving around it. I guess I said it's like a punctured complex plane, but in homotopy land, that's a circle. And you can check that sort of switching the order of the 2 points is just modding out this circle by halfway rotation. So it's just a circle that's half as long. So this is, again, a circle. The other ones are a little bit harder to describe exactly what they are. But here's the thing. If you have computed a cohomology of a space before, it's probably of the circle. And then you know that the circle has one dimension of cohomology in H0 because it's connected, and one dimension in H1 because there's only one way to draw a loop on it, and then nothing else because it's only a one-dimensional space. There's no room for anything else. And so what you can think of Arnold as saying is that even though this space certainly gets more and more complicated as n gets large, it gets higher dimensional, like more crazy stuff can happen in the braid group. From the point of view of homology, the first one is the complex plane, the second one is a circle, and then they're all circles from then on. I mean, it just doesn't change when n grows. So this is the beginning of a story that is a very, very rich story in topology, which I'm mostly not going to tell today, called homological stability, saying that even spaces that are in fact getting more complicated in homology are sort of always staying the same. But let me just tell you, why did I even bring this up? What does this have to do with the original problems? So the engine for all of this is what's called the Grothendieck-Lefschetz trace formula, which I am not going to state to any degree of precision, nor am I going to explain the numerous hypotheses that have to be checked in order to make the argument I'm about to make. I'm going to sweep it all under the rug and just say that this story, developed by Grothendieck of étale cohomology, allows us to relate the number of points on a space over a finite field to its cohomology. Now, I made this space over C, but let's not forget, this description, it makes sense over the complex numbers, but it makes just as much sense over a finite field, right? I can certainly look at, over a finite field, a set of polynomials such that this discriminant does not vanish. So in fact, let me go back to this, and I'm going to express this another way. This is just the number of points on this space over a finite field. In other words, the number of solutions to this, the number of points on the variety defined hereby. And so righty, here's what we're going to say. Applied to this variety, the number of points over FQ is going to be, I don't know, some kind of like big, massive alternating sum of the trace of Frobenius, whatever that is, on some kind of atomic cohomology, whatever that is, of conf n. But the good news is that under favorable circumstances like this one, this kind of cohomology developed by Grothendieck just completely agrees with what we compute topologically. And so what looks like sort of some kind of crazy infinite alternating sum, or very long alternating sum of stuff that we have no idea what it is, actually has only two terms. So in this case, it is the trace of Frobenius on H naught minus the trace of Frobenius acting on H1. These things are so explicitly described that I can just tell you what they are. And guess what? This is q to the n. And this is q to the n minus 1. So this is kind of cool because, first of all, it gives somehow an interpretation of what just looked like a number. But now we see that the sort of two pieces each mean something. This is tracking the H naught of a certain space. This is tracking its H1. A lot of phenomena that we see here, like for instance, did anybody notice there's a difference between these two columns? This guy has some error term. I mean, the answer to this question is definitely not exactly zeta 2 inverse times x. Here, there's no error term. And what that's reflecting is this kind of amazing fact of Arnold that there's literally no cohomology beyond H0 and H1. That, by the way, is sort of a bit of an accident, and if I were working over a more arbitrary ring of sort of some more complicated one-dimensional ring, I would see an error term, but I would be able to understand how big it was in terms of this kind of analysis. Okay, so this is actually, if I had filled in all the details that I didn't tell you about, which would take another hour, a proof that there are q to the n minus q to the n minus 1 square-free polynomials, monic of degree n over fq. It's quite possibly the hardest possible proof of that fact, which can be checked like elementarily and combinatorially. I mean, you don't even have to do any zeta functions. I mean, you can sort of do this by combinatorics. But I bring it up just to sort of show you in one very elementary case how the whole process works. That that the problem that starts over here is transformed into a question that's really about topology. And the answer to this topological question, in this case, we already knew the answer over FQ, but it gives us some insight into the structure of that answer and what it means. If we didn't know the answer, it might give us a good way to predict that answer. And under favorable circumstances, it even gives us a way to prove something over here. What usually is not the case is that we can't get all the way back. What can I tell you? Nonetheless, if we believe in this analogy, proving things over here can give us ideas for what's happening over here. I think of it as sort of a conjecture machine to make geometrically motivated conjectures about what's actually happening over the integers. I mean, maybe shall I read an inspirational quote? Okay. So of course, this analogy is really due to Weil, and here's what Weil says. So this setup of the three columns is, of course, due to him. And he writes, the mathematician who studies these problems has the impression of deciphering a trilingual inscription. In the first column, one finds the classical Riemannian theory of algebraic functions. Okay, so for me, that's actually the third column, but that's okay. The third column is the arithmetic theory of algebraic numbers. That's number fields over here. The column in the middle is the most recently discovered one. I mean, this was in the 40s, so it was recently discovered at the time. The most recently discovered one, it consists of the theory of algebraic functions over finite fields. These texts are the only source of knowledge about the languages in which they are written. In each column, we understand only fragments. So somehow the goal is to sort of put those fragments together into sort of something resembling a picture. So, okay, I hope now I've sort of said what I mean by geometric analytic number theory. And this, in recent years, has really become a sort of great industry for like all kinds of questions. I'm just going to like write a long list of names. People like, well, I guess I started working on this stuff with Akshay Venkatesh, and whose name I can spell because we've been working together a long time. and Craig Westerland. And then there's lots of work by, I hope I don't forget anyone, Alexei Entin, Efrat Bank, Eva Rodderty-Gershon. I'm going to also write some people not from Israel too, but I'm going to write a lot of Israeli people for a moment. Lior Berry-Soroker, Zev Rudnick, Paul Pollack, Dan Cardon, et cetera, et cetera, et cetera. So this has been sort of quite an industry. I'm going to talk about two rather new results today that I haven't talked so much about before. They don't actually have anything to do with each other, but they're just like the two latest things that I would like to tell you guys about. Before I do, though, actually I want to make a point about Q. Not big blackboard bold Q, but little Roman font Q. So, OK, a moment of Q. So here's the thing. I want to emphasize that by going from here to here, we have done something like a little bit weird, because we started with a question about one specific field, the rational numbers. But this is not like really one field, because I didn't tell you what Q was. Like Q could be any prime power. So really this is a question about a whole family of fields. And that extra knob that you can turn actually does bring us an interesting new element to the story, which is not present in classical analytic number theory. I suppose you could sort of imitate it by taking all these questions and saying, oh, I want to kind of think about this for, let's say, all cyclotomic extensions of Q at once. But nobody ever does that, right? I don't think so. It would be interesting to do. OK, so the second column is really not about just one field. But a whole family of fields. And that gives us the freedom to say what happens if little q gets very large. And the reason that's useful is because of a very deep theorem of Weil, which is ubiquitous in this story. So I'm not going to state Weil's theorem, but I'll just tell you sort of what we know as a result. If x is, let me just say the proper word here, is a geometrically irreducible, but if you think connected, you won't be far off, variety over fq of dimension n, then, OK, so the form of the question, as in this problem we just discussed, is always going to be to count the points of some variety over a finite field. And the statement, I mean, somehow if you had to guess how many points an n-dimensional variety over a finite field had, there's not so many good guesses, right? Maybe the only one you could think of is just n-dimensional space, and that has q to the n points. That seems like a good guess. And indeed, it is a good guess, as long as q is large. So I mean, the content is that if I look at x of fq and divide by q to the n, this just could be anything, but the limit as q goes to infinity is going to be 1. And more generally, if this were not irreducible, this limit would be basically remembering the number of connected components. You might remember I mentioned the word number of connected components before. That's the dimension of this h0. So another way to say it is that as q gets large, you have this crazy large infinite sum, and it turns out that everything beyond h0 becomes negligible. So everything I told you had to learn about, you don't actually have to learn about, and you can just think about h0 and computing connected components of things. So this is a very important tool. Doesn't matter. This is OK even if it just starts life over fq.
So you could have your variety, you could have the next column of the group enormous, no? It's not possible?
It could be absolutely enormous.
But if x varies with q, imagine, for it, you take the sequence of q and you take a sequence of
Okay. Yes, you are right. So there's different ways to say it. So one thing I could have meant, but I certainly didn't actually write that or anything, would be that I could take x over fq, and then this could be like increasing in powers of that q. That's one thing I could be doing. But you're right that in practice, what I usually mean is exactly what you said, Philippe, that I have something which is over z, and then I reduce it mod various q, and then what Philippe is quite rightly pointing out is, how do I know that there's not like a dimension like q factorial cohomology group?
sequence of curves of increasing genus.
Right, so how do I know that? I just know. No, I mean I do know because there's kind of completely general nonsense theorems that say that apart from some finite set of primes, like it basically looks the same on every prime. So you don't, yeah. That's one of the many things I'm sort of sweeping under the rug that you do, that some smart person has to have proved like 50 years ago, 40 or 35 years ago, to make sure everything is okay. So for instance, let me just say the sort of rather uninspiring consequence that that gives you for this problem that we just discussed. So suppose I didn't know Arnold's theorem. Suppose all I knew was that the configuration space comp n was connected, which we could easily figure out. So e.g., the limit as q goes to infinity of this thing we were trying to compute over q to the n equals 1, which is true because we computed this is 1 minus 1 over q. So, okay, what this says is not very impressive. It says that if I let q be very large, the probability that a polynomial over q is square free goes to 1. Okay, I mean, that's true, and it's not so surprising. I mean, that's sort of, if q is very large, the probability that the discriminant, which is an element of fq, is 0, like should go to 0. But we're going to talk about some cases now where even already this kind of has a little more content to it. And certainly in many of the results gestured at above are in this large Q regime where you really do learn things that are not so evident by any other means. Okay, so let me now take the rest of my time and kind of just introduce you to a couple of newish theorems. Let me say geometric mala, or maybe geometric mala linic. Okay, so we're sort of shifting gears now. And what I'm going to talk about here is joint work with Tang Tran and Craig Westerlin. This is a paper that just went up on the archive last month. And very much sort of building on my earlier work with Akshay and Craig. And this addresses a very old question in number theory. I mean, the basic objects of algebraic number theory are the number fields. And a basic question about those is how many are there? Okay, let me explain how to make that into an actual question that we can ask. So question, this is in column 1. How many degree n extensions of Q with discriminant at most x? So for instance, when n equals, actually let me say degree d. I think that's what I want to. So when d equals 2, actually this is the question we just discussed, because a quadratic extension just is q adjoin root m with m square free. I mean, there's some kind of nonsense about powers of 2 that I'm going to ignore, but basically this is what it is. So if we want to count how many different quadratic extensions there are, we're counting how many different square free extensions there are. And we just did that. And so we know that it's a positive constant times x. So some constant times x. And the conjecture, which some ascribe to Linick, is that well, let me introduce some notation. If nd of k is n d of k comma x is number of degree d extensions of k with discriminant less than x, here k is just some arbitrary number field, then the conjecture is that n sub d of k discriminant less than x is asymptotic to some constant, certainly depending on d and k, times x. But this is actually kind of an amazingly audacious conjecture because, how would you make a degree d extension? I mean, you would write down a degree d polynomial, right, and adjoin its root to q. That would be one way you could do it. Of course, there are a lot of degree d polynomials if d is like 100 or something. On the other hand, you want the discriminant of that field to be less than x. And the discriminant of a degree 100 polynomial, as I mentioned, is some gigantic polynomial in the coefficients of some very high degree that no human knows. And that would be expected to be extremely large, which seems like it would be very hard for it to be less than x. And I think if you just kind of sort of sat and contemplated it and were like, do I think the rate of growth of this function in x should go up as d increases, or should it go down as d increases? I think you would probably find it hard to make a good guess. And Linux says, actually, it does neither. It's just always x. The only difference is the constant. That's quite amazing. Even more amazing, this might actually be true. So very little was known about this for a long time. And of course, as most of you probably know, well, OK, so d equals 3 is a theorem of Davenport and Heilbronn from the 70s. Then progress stops for a long time. And then in a major breakthrough, the cases d, 4, and 5 were proven by Manjul Bhargava. That is true. Well, OK. Oh, yeah, so Davenport Heilbronn proved it for q, and then Datskovsky and Wright proved it for an arbitrary k, in fact, function fields too. Here, I never remember what's actually written down. Bhargava wrote it for q. It all works for k. Is it, do you know, Frank, is it written down at this point? OK, I'm going to put them down then. Who's the last person? OK. And that's it. For d equals 6, we have no idea. And in fact, I mean, so in fact, the best upper bound, so general d, there's a result of myself and Venkatesh from, I guess, 2005, the first thing we ever did together, which gives an upper bound on order, it's something like x to the x of c root log d, or something like that. The sort of trivial bound for the 19th century is sort of on order like x to the d over 4. So this, I mean, this is better than that, but I mean, I guess, this grows more slowly than any power of d, but it grows more quickly than any power of 1, which is what it's supposed to be. So it's so this is all we know. So let me OK, good question. So what I'm going to do in 1 second is say, what if we specify the Galois group? So if I say here, I'm only going to count those degree d extensions whose Galois closure has Galois group SD. Then there's an explicit prediction by Manjul for all d, which agrees with what he proves for d equals 4 and 5. I think there are actually rather interesting subtleties, which actually I have written about what the exact conjectured constant should be for a general Galois group. I think with sufficient stamina for a particular group, you could work out something that I would believe. OK, so let me just say, I didn't mention Molly yet, so I'll just say, more generally, let G be a subgroup of SD. And now, write n of kxg is the number of degree d extensions with discriminant less than x. But now I require that when I look at the Galois closure of this degree d extension, which is a subgroup of SD, I want it to be this group G. Equals G. And then the conjecture of Mala is that oh, sorry, yes. And here, of course, I really mean like the Galois closure or whatever. Sorry about that. Yeah. So Mala conjectures is for any number field. There's sort of a weak version and a strong version. I'll sort of state the weak version. He says that, okay, there's some power of x, and this number is between x to this power and x to this power plus epsilon. And this is explicit in terms of the group. I'm not going to sort of go through it, but it's some explicit number that he writes down. So in particular, when G is SD, in order to conform with existing conjectures, he certainly would conjecture that something slightly weaker than, I guess it would say, when G equals SD, of course, A of G equals 1. And I'll say there is a stronger conjecture that Mala makes, actually, which is that he gives you instead of writing just plus epsilon, he'll give you an explicit power of log, which he believes is it's x to the A of G times log to some other explicit power, B of G. It doesn't depend on. That's right. Well, D is implicit in G. So D is hiding in the notation because G is a subgroup of SD. So, but certainly, I mean, the point is this is certainly never bigger than 1. That would be a disaster for the other conjecture, because then there would be too many. So it's, yeah, it's always 1 over an integer, in fact. And you can check, by the way, that you can't get away with not having this epsilon. There are cases where you see powers of log. So if you don't like any of the geometry, think about why for Z mod 2Z cross Z mod 2Z extensions, there has to be a power of log in the. Okay, so let me state a theorem. Which is that for all Q bigger than some constant depending on the finite group G, if I look at n of fq of t, xg is less than or equal to some constant times x to the a of g plus epsilon. So in other words, we recover the upper bound in Mala's conjecture. And in particular, it follows that the number of degree d extensions is bounded above by some constant times x to the 1 plus epsilon. So we recover the Linux conjecture up to a plus epsilon. So this is much, much more than we know in the number field case. A couple of comments. One, this is not quite the same as letting Q go to infinity. We have to make Q big enough, but once you make Q bigger than some constant, this x can grow. So this is kind of intermediate between any Q and Q goes to infinity. It's Q large enough but fixed. So let me say just a word about sort of what goes into proving something like this, and then I want to talk about, I was like really jazzed about Maxime's talk, and I want to talk about sums in short intervals. So I'm going to say one more word about this, and then we're going to talk about sums in short intervals.
Does this actually work for extensions of FQT also, or just for?
Great question. This proof really works just for FQT. Again, I think a person with stamina could maybe make it work. But definitely the way we set it up, it's really using that it's FQ parentheses T. So let me just say what the 3 columns are in this case. So, well, I guess you sort of know what column 1 is like. Just for simplicity, I'm not going to write a general G. I'm just going to write this and D. So this would be like counting degree D extensions of Q. Column 2 is counting degree D extensions of this field, but now some geometry begins, because a degree D extension of this field, which I'm going to think about as the function field of a rational curve over FQ, this is the same as the set of degree D branched covers y to P1 all over FQ. And this is where algebraic geometry comes in, because these guys are parameterized by a moduli space. So column 3 is the Hurwitz space parameterizing degree D branched covers y to P1 over C. And in fact, once you sort of make this identification, in fact, the large majority of this like 67-page paper has nothing to do with number theory at all, and is about the topology of this space. That's where the work actually happens. So maybe I'll say, I'm not going to say at all how we control the cohomology of this space. Let me just talk about my favorite one, H0. Maybe it's your favorite too. So note that, so what if I just say, what is the limit as q goes to infinity of, now I'm, instead of x, because here, as in the case we discussed before, this discriminant is always going to be a power of q. So let me write x equals q to the n again, and I'll write q to the minus n times the number of extensions of discriminant at most n. So if I cover up the limit, like, this is the thing that's supposed to be approximately 1. And we can ask, well, is this true at least if I take the limit as q goes to infinity? But now, as we know, this is somehow a question about the connected components of a space, namely this space, right? Because this is counting points on the Hurwitz space over FQ. To say that its number of points is approximately q to the n is exactly to say this space is connected, and indeed that's true. So this is 1 because the Hurwitz space is connected. And unlike in the case of configuration space, this is definitely not obvious. In fact, the reason that these spaces are called Hurwitz spaces is because Hurwitz was the guy who proved that they were connected. He invented them to show that the moduli space of curves was connected, that you could get from any genus G curve to any other by continuous deformation, which was certainly not obvious. This wasn't obvious either, but he proved this. So in some sense, this original theorem about Hurwitz spaces is sort of the first thing that you would do in this problem. And at least for me, I mean, this sort of goes back to stuff we thought about years ago. It wasn't until I wrote this down that I started to believe in this crazy conjecture of Linux. Because if you were like, hey, I think the number of degree D extensions of discriminant less than x should be like x squared. I don't think it should be x. That's ridiculous. It should always have the same exponent. Maybe it's x squared. Well, then you would think that this number was around q to the 2n as n gets large. And somehow it would be very weird if this grew like q to the 2n as n got large, but then for a fixed n and growing q, it was behaving like q to the n. So somehow this is like one way of thinking about how you know that this equaling this is the right exponent. And maybe I should say here, which I didn't say, is that this is it's an n-dimensional space. That's easy to see. So that's why its connectedness tells you that this number of points grows like q to the n. No, so, okay, d is the degree of the extension. Q to the n is the discriminant. So because I'm trying to suppress the topology, I'm not even really telling you sort of I mean, so what it will turn out is that n is the number of branch points. And that's what's controlling the discriminant. No, the discriminant, because now it's not the discriminant of a polynomial, it's the discriminant of a field extension. So that's just a different thing. If you like, it's like the normal sum ideal, so it's a real number. Right, the discriminant of a polynomial or of a FQ is an element of FQ. The discriminant of a field extension is a real number. So yeah, sorry, that's like a kind of an overweighting of the same word to mean two different things. Okay, so now let me, okay, I'm gonna have to very briefly say a few words about this. Sorry to use up my time. So variance of short sums. So for this thing, it turns out we can't prove a stability result. I'd love to, and for some very restricted class of groups, we did that with Akshay and Craig. But here we're settling for an upper bound. And for that, we don't need stability. We just need to get some upper bound on the dimensions of the cohomology groups, which is what we get.
And the proof, so you have this more precise result and the corollary, but you could prove the corollary without splitting into groups.
No, that corollary would come from just like writing down each group. And I mean, and just knowing that these constants are never, there's finally many of them, these constants are all at most one.
You need the splitting into the various
Yeah, the way we set it up, we sort of, the theorem is really about this situation. Okay, so variance of short sums of arithmetic functions. Okay, so I'm not really going to be able to, maybe I'll sort of talk about this rather than sort of saying it. But Maxime helped me by sort of introducing this whole subject of the question of like, what do we know about short sums of arithmetic functions? And as we saw, the sort of first way that you might get a bound on how much, on a guarantee that they're like, let's say non-zero, would be to control the variance, right? We sort of saw the second moment in Maxime's talk. So, so question, what is the variance of, let's say, I'm just going to pick one example. Let's say the sum from, I'll try to use the same notation, x less than or equal to n less than or equal to x plus h of mu of n as x varies over x to x, as we saw in the talk this morning. This question, like every question we've discussed today, has a very natural analog in the function field setting. I can do this. I can ask this question over fq brackets t. And there's a beautiful paper of Keating and Rudnick, which shows that the limit as q goes to infinity of, okay, now I'm sort of, I was going to talk about von Mangold, so I hope I get this right. That this variance grows about like h, and they even get a leading term, that this is, if I think of this as q to the little h, that we can say exactly what happens in the large Q limit. And the way this works is very much along the lines that I said, that it sort of reduces as it uses equidistribution results of cats, but it's essentially using the growth of Q to mean that you only have to compute one cohomology group instead of many. So my students, Daniel Hast and Vlad Matei, and Vlad is here, they approach this problem from a more direct algebro-geometric point of view. So more directly, they showed, okay, so Vlad, you have to yell out if I say something wrong, because I was going to do this for von Mangold. This limit existed and can be computed as the dimension of some cohomology group. And they wanted to compute it, and I wanted to compute it too, but we couldn't compute it. So I'll just close by saying, and this is, I guess, last year, 2016. And then a paper came out by Rogers, also last year, a student of sound. Wait, did I do this wrong? You're a student. Yes. Crap. Okay, I think both of you guys wrote letters for him. Sorry. Oh wait, but the year was right. Okay. Well, but no, this has nothing to do with you, Terry. Why am I writing your name here? Okay. Okay, so what they did, and this is what I wanted to say because I was excited by Maxime's remark in his talk, is he revisited Keating and Rudnick's result and showed that essentially something like this holds for every arithmetic function. It doesn't really matter what the function is. And this is very much in the spirit of what we heard this morning, that the reason it holds for absolutely any arithmetic function is that it's not about arithmetic functions at all. It's about the anatomy of integers. It's about sort of the variation of factorization types in a short interval. You prove a theorem of that kind, and you get something that tells you about every arithmetic function at once. And what's even more cool is that, so they proved Keating and Rudnick for arbitrary multiplicative functions. And from that, you can derive, you have to use the results of Hast and Mattei to get this, but you can actually compute this cohomology group, which we weren't able to compute directly by algebraic geometry. So you can read about this whole story on my blog if you want. I wrote about it at greater length. But what's quite cool is that most of what I talked about today was ways to sort of bring algebraic geometry in to give an algebraic geometric proof of a theorem in analytic number theory over function fields. In this case, and it does happen sometimes, you see the reverse, where there's sort of some fact about algebraic geometry which we prove using analytic number theory methods. Now, what is the case, and I was just talking to Will about this, Will Sawin, is that probably there's a way to sort of eliminate this circuit and go straight from what Katz did to this algebraic geometric thing. But in any event, as it stands now, it's sort of a nice application in the other direction. So I'm at the end of my time, so I'll stop there. Thanks, guys. So I think, yes. So I think that, right, so I didn't really sort of talk about it in this talk, but to my mind, one of the goals of geometric analytic number theory is to even say, if you have a conjecture on the number field side, what should be the conjecture that's purely about geometry that, so to speak, matches it, which maybe you can prove and maybe you can't. And I actually can tell you for Linux exactly what that conjecture is, and it's something I believe pretty strongly, but we don't know how to prove. Which is that this space of branched covers, right? So this Hurwitz space up here, it's some moduli space, like in algebraic geometry. It's like a space over the complex numbers. It's connected, so its H0 is just one-dimensional. I think that, at least stably, all the other cohomologies should vanish. Or maybe just H1 should be there. It should be like Arnold. Right, this theorem about the braid group that I told you, where there's just H0 and H1 and everything else is 0, that should also be true for these much more complicated spaces. If that is true, that implies Linux on the nose, like not this kind of weak version that is actually now proved, but even the strong version. It would tell you what the constant was, and it would agree with Bargava's prediction, like everything. So I think that's what's going on. I think these Hurwitz spaces have. Wait, that was Dinniker, right? Where are you? Oh, OK. I was like, I know that was Dinniker's voice, but I'm like having trouble tracking. So I think that's very believable. And in fact, your colleague, Tom Graeber, years ago explained to me that sort of under general philosophy on tautological classes, you believe that all stable classes and all moduli spaces of curves are tautological. You can show that the tautological classes all pull back to 0 on this space. So I think we can believe that for sort of number field counting reasons. We can believe it for like Tom Graeber style moduli of curves reasons. I think it's like a very plausible, and I think that conjecture purely in algebraic geometry should be thought of as geometric lintic. Yeah.
So what sort of function field analogs are there towards the weak moduli conjecture for the lower bounds?
Great question. So lower bounds. In some cases, so in the paper with Akshay and Craig, we just deal with like G essentially being a dihedral group, and there we get the lower bound. There we get it. Essentially, if you have, it's kind of like, okay, let me try to say something that sounds like analytic number theory. What we can do by bounding these Betti numbers, it's kind of like having a purported main term, but then an error term where our upper bound on it is like way worse than the main term. Okay, so that's kind of bad, but it's good if you're willing to settle for just having an upper bound, because then you just like throw the main term in the trash and you're like, my upper bound for the whole thing is my upper bound for the error term. But if you want a lower bound, then you're hosed, right? So I mean, for a lower bound, you actually need the error term to be smaller than the main term. And that would really require not just having an upper bound for the cohomology of these spaces, but really knowing that it stabilizes, and even better, knowing what it stabilizes to. And we're only there for this very restrictive class of groups that we talked about in our first paper. Yeah, Frank. Mm-hmm.
And I count them by conductor instead of discriminant, in which case the results clean up beautifully. And I'm wondering if these methods that you suggested over function fields can just as naturally count them using different invariants.
Yeah, so another nice thing about the geometric approach is that when you count things over function fields, it somehow is more clear like why the things that are screwed up. Like in some sense, if in this context you try to geometrically count D4 extensions by discriminant, as was classically done, it's like a huge mess, and what you're doing is like geometrically incredibly unnatural. You're sort of counting the wrong things. Whereas if you count by, so I don't exactly know what conductor translates into. I think they should be counted by the Wood discriminant. Like, like Melanie Wood has a very nice, like, I mean, Melanie has what I think is sort of probably, I like her way of counting. Does it amount to the same? I don't know this paper you're talking about.
Well, it hasn't appeared yet, but it's in terms of the associated Galois representation.
Yeah, but there's lots of representations of D4. Like, which one? Okay. So I think, okay, so for the fans of this stuff, I think a basic desideratum that you have to have is that whatever conjugacy class in the group you assign the lowest weight to, that conjugacy class or conjugacy classes had better generate the group, or else you're going to get something nasty. And that's what fails for D4 with discriminant. If you look at a quartic extension with Galois group D4, the ones which contribute least to the discriminant are, I forget what conjugacy class it is, but it's some conjugacy class that doesn't generate D4. And that's what makes it be some, you know, in this paper of like Henri Cohen and Diaz and Olivier, where it's this like nasty double Dirichlet. Sorry for the people who like double Dirichlet series. I forgot I was at an analytic number theory conference. But yeah, okay. So basically, I think all I can say is I super look forward to seeing this paper, because I sort of feel like I like the philosophy of this stuff, and I think yeah, maybe I should have said I don't think there's just one right way to count, but I think there's lots of wrong ways to count.
I had a quick question about your upper bound here. I mean, you said that someone with enough stamina could probably replace FQ of t by an extension, but is it the same with the epsilon? Could that be turned into a log if someone was able to throw enough at it? Or?
Oh yeah, sorry. So in the paper, it is a log, but it's like the wrong log. Okay. It's like a power that's like, yeah. So it's a power of log that is bigger than one mole gets. But yeah, but it is a power of log. I just didn't care to write it down. You could make it be, for instance, log to the order of the group would be more than enough.